Morning everybody. Today we're going to talk about DNS, the domain name system, and we're going to talk about how that actually works. We're going to whiteboard that out, and we're going to check this out on Windows Server and how this actually functions on the internet. DNS, or the domain name system, was invented in 1983 by Paul Mockapetris while working at the University of Southern California's Information Sciences Institute. The idea behind DNS was to create a system that would allow people to easily access resources on the internet by using easy to remember domain names, instead of having to remember the IP address of every website they wanted to visit. Now, in the early days of the internet, there were only a few hundred hosts connected, so the Internet Assigned Numbers Authority, or IANA, was able to manage a simple text file called the hosts file, which mapped host names to IP addresses, and we'll take a look at those later. However, as far as the hosts on the internet grew, this file became increasingly unwieldy, and a new system was most definitely needed. Mockapetris' solution was to create a hierarchical system, where domain names would be divided into zones, and each zone would have its own authoritative name server. This way, the responsibility for managing a domain name's resolution would be delegated to that domain name server, which would be responsible for resolving domain names within that specific zone. The first version of DNS was created in 1983 with RFC 882, and the current version, DNSSEC, which was published in 2010. Today, DNS is an essential component of the internet, allowing millions of people to access resources on the web using domains instead of IP addresses. So let's go check this process out on a whiteboard solution, and we can then go and move that into looking at more practical demos. Let's start off with Bob. So Bob is down here on his computer, and Bob wants to go to a certain website. Maybe Bob wants to go to something like mail.google.com. Okay, so this is a full URL. Well, not URL. This is actually known as an FQDN, or fully qualified domain name. Technically, what we have is mail.google.com dot. There is actually a dot here at the end. It's hidden from you. Now, Bob's laptop is configured to go and look at something called a DNS server, which will be configured inside his office environment. We'll get over to having a look at a DNS server later. But Bob's laptop needs to go to mail.google.com, but it doesn't understand where this is. What Bob's laptop wants is Bob's laptop wants the IP address of mail.google.com to be able to send traffic and request information from it. Now, one of the first things Bob's laptop does is it looks to see if it already has any information about this on the local computer. Built into this computer, there is something called a hosts file. Now, a host file is literally just a text file. So, on a Windows machine, if we come across to this directory, C Windows System 32 drivers etc, you will find this specific hosts file. You can open this with Notepad if you want to, and what you'll see is a hosts file. The host file is configured in a way that anything that starts with a hash is commented out, it's not going to be processed, and we can insert extra records below here. So say, for example, if we always wanted to send google.com to our local host, we could do 127.0.0.1 and do a tab and do www.google.com. The problem then is if I do save this, my computer will always use this hosts file, even if it's invalid. So in this case, google.com would always fail to load because my computer would never check the results of this host file. It would always use 127.0.0.1. This can be an incredibly useful file later on if you want to redirect how things are actually routed inside your environment. Let's go back to the whiteboard. So back here on the whiteboard, our computer has checked this host file and said, hey, do you know where mail.google.com is? There is not an entry in the host file, so the next thing it needs to do is actually contact its local DNS server. Now, this local DNS server is normally located inside your office environment, and we will take a look at one of these things in a moment. If this is not operating in an office environment and you are in a home environment, your local DNS server is actually probably going to be your router, the thing sitting in your house, to connect you to the internet. The problem is that this is not really doing proper DNS. This is actually just going to be forwarding your information or your request to somebody else. Now with a proper DNS server, what's going to happen is this laptop is going to request and say, hey, do you know where mail.google.com is? And this DNS server, whether it's in Linux land running on something like Bind, or it's Windows land just running Windows DNS services, which we'll take a look at in a moment, it will come back and say, no, I don't know where mail.google.com is, because I only know things related to my specific DNS zone, the one I'm responsible for, which is normally going to be for the office or the company that you're currently working for. Now, what this DNS server does have built into it, though, is something interesting. Let's take a sip of tea first. Every DNS server out there has these things called the root server list. Now on the internet, out here in the big wubby over here, which is where we essentially want to get to eventually, there are these things called the root servers. Now the root servers, there are a sum total of 13 of them. There are only 13. If we have a look at the Wikipedia article for root servers, you'll be able to see a list of these 13 root servers down here, from A all the way through to M. Now there are many more than 13, they are actually replicated into multiple locations around the world, but these are the actual sources. Notice some of the people who are actually responsible for managing these services. People like NASA, and people like the US Army Research Lab, and there's two that are run by VeriSign. These are all actually located in the US. Our root server list here inside our DNS server, it doesn't change. Okay, these are hard-coded IP addresses inside the DNS server for these root servers on the internet. So what my what my DNS server actually does is it kind of backtracks. It says, okay, Bob over here wants the IP address for mail.google.com dot, and that dot, remember, is denoting the root of the internet. So the DNS server says, right, I don't know where these are. Let me go and ask the root server. And it says to the root servers, or any of the root servers that respond, it questions them and says, hey, do you know where mail.google.com is? And the root servers come back to this DNS server and say, no, we don't. But what we do know is we do know what the location of something called the TLD servers are, the top level domain servers. So these root servers know information about the location of things like the servers responsible for COM, the servers responsible for FR, the servers responsible for org, the servers responsible for DE, who you probably know, France and Germany, and the servers responsible for people like CH, which is Switzerland, because Confederatio Helvetica. And there's even some strange ones out there. Sure, there's ones like .ninja and .pirate, which you can actually buy now as top-level domains. You can also buy things like .london, but there's some old ones that are quite outdated, shall we say. For example, there is a .su domain name. Now, this .su domain name, if you're sitting there thinking, oh, well, this might be Sudan. No, this is actually Soviet Union. And yes, you can still buy a .su domain name, but amazingly enough, it's now actually handled by the Russians. So, what this DNS server then does is it goes, okay, fine, I'll go and contact the COM server instead. And it says to the COM server, excuse me, do you know the location of mail.google.com? The COM server responds and says, no, I do not know. But I do know where Google is residing and who is actually responsible for that zone. So this DNS server now goes out and it goes and finds this server belonging to Google, or more to the point, Google's DNS services. Now, Google are big enough to run their own DNS servers on the internet, Most people are not. At this point, if you register your own domain name, like I have michaelwhitehouse.com, and register that through something like GoDaddy, this would redirect to GoDaddy, who will be responsible for your DNS zone on the internet, your collection of records underneath your DNS address. So it now says to Google's DNS, do you know where mail.google.com is? Google goes, of course I do. I know where mail.google.com is. I know where YouTube is. I know where calendar.google.com is. I know where docs.google.com is. I know all of this fun stuff. What do you want? Okay, let's go and look at the mail.google.com address, IP address, and we will pass that back to this DNS server. This DNS server then finally actually passes that query back to Bob. What you've actually got is two types of DNS queries going on here. Okay, in this example, where Bob is communicating to the DNS server, this is known as a recursive query. Over here, on the other hand, where the DNS server has communicated to the root servers and the COM servers underneath, this is known as an iterative query. The difference between these is that with the recursive query, Bob down here has sent a request to a server and has received a complete answer. On the other hand, with an iterative query, this has actually sent a query to another server and received a partial answer, a redirection to somewhere else within this structure. So let's go and have a look at some of the concepts like this and some of the settings that you might need to configure on a Windows server. So we have here a Windows Server 2022 machine, and we are going to make this into one of our DNS servers to play with. So I'm going to come up here into Manage and Add Roles and Features, and we're just going to very quickly click View Next on here, and we're going to install the DNS role onto this server. Let's go next on that one, next on that one, next on that one, and install. There was a slight complaint there about not having a static IP address for the server. That is because this is going to be a demo, and this virtual machine is currently running in Azure, so it will be receiving a dynamic IP address. I could set this as a static IP address if I want to, but I'm only doing a demo here. So now our DNS server is installed, we can go and run it. We can go and click on Tools and DNS, and up here we will see we have our DNS Manager. Now within this DNS Manager, if we open it up, we have forward lookup zones and reverse lookup zones. Now these forward lookup zones allow me to respond to requests for IP addresses. So if I go in here into right click and create a new zone, I can create whatever zone I want. I can create primary, secondary, or stub zones. Let's just stick with a basic primary zone. And let's call this adatum.com. Okay, and this is going to create a new file, and we're not going to bother with any dynamic updates. And here we have a very basic DNS zone. This is not valid on the internet. This is only valid for people who are actually calling this specific DNS server. So we're going to create a record in here. Now there's a number of different records you can actually create, including A, AAA, CNAME, MX records, pointer records, and so on and so forth. If we go into other new records, you'll be able to see there is quite a few. Most of these today are not actually used anymore. But I'm going to concentrate on just a very basic record. I'm going to concentrate on a host record. And we're going to call this test. And we're going to give it a very testy type IP address. We're going to use 10.10.10.10. Okay? But notice we have test.adatum.com. And we're going to add that host in. Now let's just also look at something else on here. When I looked at the whiteboard, I did say that the DNS server had information or knowledge about the root servers. We can see that here. If we go to the properties of this server and we look at this section here that says root hints, you'll see all 13 DNS root servers already pre-built in here. Now, let's go and have a look at a client computer. I have a Windows 11 client computer here. If I go and run a command prompt, I can run a number of different commands to resolve IP addresses, but the one I'm going to use is nslookup. If I use nslookup and just do www.google.com, this is actually going to return an answer for us of 142.250.180.4. This is actually using the DNS server that is currently configured for this machine. If I do ipconfig/all, you'll be able to see that there is actually a DNS server configured here, 168.63.129.16. This is actually a very important IP address, as this is the IP address of one of Azure's internal DNS servers. We want to kind of change this. Now, since this IP address is pointing to a DNS server that exists in Azure, we might actually want to resolve it from a different server. We can do that with NSLookup as well, or name server lookup. If we look at this command itself and press enter, we can actually jump straight into it. Now, if we do a question mark here, there's a whole bunch of different options we can go check out with NSLookup. And one of those things that we can actually do is we can actually specify the server name that we actually want to use to resolve this information. Now, our server over here, our Windows Server 2022 server, the IP address is 10.0.0.5. It should be on the same network as my Windows 11 client. So if we do an IP config over here, you'll notice this is 10.0.0.4. So now, if we do a lookup, like for example NSLookup, and we do www.google.com, and then give a server of 10.0.0.5, we should be able to see we have a result. And this result has actually come from my DNS server running on my Server 2022 box. To prove that, we can also go and NSLookup the record that we created, test.adatum.com, and we can see that that is actually returning 10, 10, 10, 10. If I did not use that custom server on the end, this would attempt to actually resolve this on the internet by using Azure's DNS servers. This is not going to work because test.adatum.com is a test domain that's actually owned by Microsoft and is not on the internet at all. So we can see that what's actually happened here is in two locations. In this example, test.adatum.com has been retrieved from here, from our forward lookup zone and from adatum.com. And in the second example, when we selected go and get google.com on 10.0.0.5, this has been returned off the internet. So we're going to look into this in a little bit more detail. Installing Wireshark, as I have done here, onto the server will allow me to filter for just DNS traffic and see the raw information going in and out of that server. So now if I type NSLookup google.com in here, you'll notice there's a whole bunch of traffic that has been created, including communications between this server and the actual DNS server belonging to Azure. Now, let's go and look at the traffic coming from the other direction. So let's refresh this information here, continue without saving, and we'll go back to the client computer. And let's try sending this same thing, NSLookup test.adatum.com, and run that. Now if you run this and come back to my server, you'll notice there's a whole bunch of queries here where it's actually gone and said, hey look, there's 10.0.0.4 communicated to 10.0.0.5, and here is test.adatum.com and the raw packet itself. So what we can also do is we could go and say, hey, let's go and get not test.adatum.com, but let's go and get google.com and run that same query from here. If we go back to our DNS server now, there is a lot more traffic has actually been created. But what we can also see is that we can see this request actually coming in from 10.0.0.4 to 10.0.0.5. And what we can also see is we can see these requests going out of 10.0.0.5 to the DNS servers that exist on the internet, and return that result back to this server, back to 10.0.0.5, and then from 10.0.0.5 sent back out again to 10.0.0.4. We can see that full DNS resolution inside here. Now, if you want to play with Wireshark yourself, this is actually a free open source piece of software, and you can go and download it. You also need something else installed called the NPCap driver, and this driver will allow you to actually investigate traffic with Wireshark. So that kind of concludes a basic introduction to DNS and actually seeing how DNS resolution works on the internet and with a DNS server working locally on your computer. I hope you enjoyed this, and you'll join me next time for more interesting IT content. Have a good day. And you know the routine, hashtag like and subscribe, and I hope you enjoyed this video and will join me next time. Goodbye.